So for today's session, I'm going to talk about topic 4, which is DC machinery fundamental. Okay, so basically we have done introduction of the machines, and then that one is in topic 1, and then we proceed on topic 2, which was about transformer. Okay, discussions about the transformer. And then topic 3 we have just finished last week. Last week mean the week before your semester break. Okay, we have done topic 3, which is AC machinery fundamental. So we have discussed transformer, AC machinery fundamental, and then today in this session we will be discussing on the topic 4, which is DC machinery fundamental. Okay, so basically in principle DC machine, what is inside the machine is actually the same as the AC machine. So the thing that the difference of a DC machine as compared to the AC machine is actually in terms of commutation. So we will learn about the commutation process of DC machine after this. Okay, there is a subtopic here that we will discuss on the DC machine, how to get the DC voltage out of the rotating loop by using commutator and brush. All right, so maybe I will show there is a video as well. So I will share the video that shows how the commutator works in DC machinery. But before that, all right, we will start from the beginning. Okay, so basically the outline of this topic 4 consists of 3 subtopics. Okay, which is 4.1. I'm going to talk about the simple rotating loop between curved pole faces. So what does it means by curved pole faces? We will have a look later. Then from this a simple construction of the machine, we are going to discuss on the voltage induced as usual. Okay, we are going to discuss on voltage induced in rotating loop. So we have curved pole faces and then rotating loop, and then from that rotating loop which has the segment of AB, BC, CD and DA, we will derive on how to get the induced voltage across the terminal at the rotating loop. Okay, and then the second one, we will be discussing on the DC voltage out of the getting the DC voltage out of the rotating loop. Basically in that rotating loop, what is happen is it will induce the voltage in the form of AC sinusoidal voltage waveforms, something like that. But from that AC waveform, we are going to extract, or we are going to transform or convert it into DC by using what I've just said earlier, which is using the commutator and also brush. Okay, so just by using commutator and brush, we can convert the AC output of the DC machine, or of the AC machine, of the machine, right? I'm just going to use this general name lah, for the machine, which is the AC machine. Then we use the commutator to convert that AC behavior inside the machine to the DC machine, okay, to the DC output. All right, so and then when we talk about induced voltage in this case, basically it's about the generator. Okay, so in general, when we talk about machine, basically is that machine working as a generator or motor? Okay, that two questions. When we refer to a machine, is it machine in terms is it the generator or motor? Okay, so when we talk about voltage induced in the rotating loop, this is basically referring to the uh, generator. Okay, so when we rotate the loop at angular velocity of omega, what happen is the voltage will be induced across the segment, each segment of the wire loop, and then we will calculate that induced voltage across the terminal of that wire loop. So that sort of thing basically refer to the uh, generator action. Okay, and then the third one, as you can see here, is the induced torque in the rotating loop. So when we talk about torque, basically what we can imagine is the force. Okay, because torque is the radius time cross force, right? So basically, when the force induced, of course, the torque also will be induced. And then when we talk about torque, basically it is the action of the motor, which is when we pass through the current to the rotating loop, okay, the wire loop. What happened in that instant is if that wire loop is inside the uh, magnetic field, what happened is the torque will be induced that uh, making sure that the rotor or the wire loop is keeps rotating. Okay, so that wire loop will be rotating because of that torque when we supply current to that wire loop. And then section 4.2, we are going to explore more on the commutation in simple for loop DC machine. So as you can see, this is for loop DC machine, meaning that it has four wire loop in that DC machine. So that is the most basic construction of the DC machine, which is it should have at least four loop, okay, four wire loop. So in this part, in the first part, the earlier part, basically we are talking about more conceptual based design, which is just using the single wire loop, all right? But for the actual DC machine or AC machine, it should have more than at least four wire loops, okay? So in this case, so for the DC machine, the four loop DC machine, we'll be talking about it more later in this section. And then the third, which is the third section, 4.3, problem with commutation in real machine. So when we considering the real machine, of course there will be some problems of the real machine that will be further discussed on, especially in terms of current. Okay, normally when we talk about machine, when you have machine, when you see the actual machine when it is working, normally what we can see from machine is something that spikes. You can observe some spikes. Some spike when it rotates. We start to rotate, there are some spikes. That spike is also some of the one of the problems that occurs in terms of brush contact between brush and commutator. So it will produce some sparks because of the starting current. All right. So that is the outline of this topic. So we are going to explore for our first section, which is the simplest DC machine construction. It should looks like this. As you can see here in this image, right? It is something similar that I have drawn in my lecture notes here. As you can see in my lecture notes, which is the similar picture of this one. So which is this one is much more simple, which has the north side and south side of the magnet, which is the permanent magnet, if built in such a way which is looks like the curved pole faces, the north side and also south side. You can see the curvature design of the pole face. Okay, this is the pole face which is curved, and then also similar to the construction of the south side. All right, so we place this wire loop inside this curved pole faces, and then what we do is basically we turn this wire loop to the counterclockwise direction. So we turn this wire loop to the counterclockwise direction. So what happened, basically we don't supply any current, okay, just a wire loop and magnetic field inside this machine. Okay, so we turn this wire loop to the counterclockwise direction based on omega m, which is the angular speed, which is the mechanical speed of this wire loop is omega m. All right. So as you can see at the bottom figure here, also shown that when we rotate this wire loop counterclockwise direction based on omega m and omega m angular speed, all right, what happen is the voltage will be induced at each of the segment. For example, we can just refer to this figure. We can say that the voltage will be induced across AB, which is EBA here. Okay, and then across BC also, we assume that voltage will be induced, but actually when we calculate, there will be no voltage across BC. Okay, no ECB. ECB equals to 0. But as you can see here at segment CD, we assume that the voltage of EDC will be induced. Okay, so we have EBA and EDC. Then so just imagine that the voltage will be in that direction. We assume that the voltage will be in that direction, okay, in the corresponding direction as shown in the figure here. Okay, so basically when we want to determine the direction of the voltage induced, what we are going to do is to use our left hand rule, right? Left hand rule to determine the direction of the voltage. So let me just show you, okay, in the next page of this lecture notes. Okay, as you can see, if from that construction of the DC machine given in the earlier page, all right, as you can see, this is the figure of the magnetic lines, the flux line, the magnetic lines, or the magnetic field lines, that we can observe of a machine if we have a look at this machine from back. For example, if I have my eyes, if I put my eyes over here, right? So what I can see from the back is something like this lah, something like this, which is basically you can see that the north pole and then south pole, right? And this is the rotor with the wire loop, all right? Rotor with the wire loop. So basically the flux will be flowing from north to south, right? But as you can see clearly here, as it is written here, it is drawn here, you can observe that the 90-degree angle, right? 90-degree angle of the direction of the flux vector, 90-degree angle out of for example, in this case, in this example, so you can see that 90-degree angle of the flux lines out of the north pole phase. Okay, and then when this flux lines enters rotor, it is also perpendicular. All right, so we can imagine that if we have stator and we have rotor and the other stator, what happened to the flux line is something like this, which is from stator to the rotor, it is the flux line which is perpendicular. All right, perpendicular, get into the rotor, which is something like that, then out of the rotor back to the south pole stator. Okay, so that is the behavior of the flux of this rotor inside the curved pole faces. So we can observe the phenomena something like this, and then back to the rotor, which is the rotor construction, which is in this page, in this figure. At the bottom of the figure, you can see this is the rotor construction with the wire loop the right hand side wire loop and then the left hand side wire loop. The right one refers to the AB segment, the left one is CD segment. So what we can see at the AB segment, we are going to calculate the induced voltage, which is EBA. So how do we know that this EBA is into the page? Okay, why this EBA is into the page? Because as you can see, when we use the right hand rule, you can use your right hand rule now, and then try check. Is it correct that EBA is into the page? So as you can see, your thumb is the velocity. Okay, your thumb is the velocity VAB, and then your index finger is the induced voltage, and B is the middle finger, the hantu finger. The middle finger is B. So if you use your right hand rule, then you'll see that, actually the EBA is into the page for this segment. For the EDC is out of the page, which is CD segment. At the CD segment, the induced voltage is out of the page using the same method, which is using the right hand rule. All right, so now we have already know that the induced voltage for the AB segment and CD segment. What we can do now is to calculate the induced voltage at each segment so that we can compute the total ETOT, or total voltage induced across that wire loop. So we calculate segment by segment. As you can see in this case, for segment AB, we calculate EBA, which is using V cross BL. So since all of the components, V component, B component, and L component vector are in the right angle, which is perpendicular to each other, we can just directly calculate it using VBL. Okay, so VBL voltage induced is the voltage under the pole faces, which is, as you can see on the left figure here. So VBL is actually the voltage across south pole faces. Okay, in this case, the voltage across south pole faces. So the voltage under the south pole faces is VBL for segment AB. Okay, for segment CD, we are going to I'm going to explain segment by segment. Okay, that one is segment AB. All right, so we know that at the segment AB, induced voltage is VBL. Okay, but when AB reach the place where there is no flux, which is at 180 degree, which is here, is 180 degree. Sorry, that is percent. Okay, when AB segment is at 180 degree, AB, BC, CD. So let's say it start from AB start from here, and then it rotates. Under the pole faces here is VBL. Okay, when AB turns and reach to 180 degree rotation, what happened at that segment is 0. So at this instant, AB segment is 0. Okay, as you can see here, no flux at this segment, at this top and bottom segment. So when AB segment reach this area, so there will be no flux, will be cut down, and then no induced voltage at the moment, at that moment. Okay, so we can say that at 180 degree and 0 degree instant, induced voltage across AB, which is EBA, is 0, except under the pole faces. Okay, under the pole faces, induced voltage is VBL. Okay, so when we calculate the voltage induced at the segment BC, okay, let's say Let's say this is the wire loop. So segment BC referring to this segment, right? So what happened? Since the quantity of V cross B for segment BC here, the quantity of V cross B is perpendicular to L. So, okay, L is to that direction, right? That is L. But in this case, V cross B is perpendicular to direction of L, meaning that there will be no voltage induced. So in segment BC, from our experience of calculating the system or the construction of the AC machine as well, when we calculate the segment by segment induced voltage, of course we know that across this BC segment there will be no voltage induced. So similarly for the DC machine as well, under at the BC segment is no voltage will be induced. And then the third one we are going to calculate for the segment CD. So similarly for the segment AB, induced voltage at segment CD is also same. Okay, also the same, which is VBL under the curved pole faces. Under the curved pole faces, which is under this area, segment CD is VBL, except when that segment CD reach 180 degree or 630 degree, for example. In that case, it is 0, right? So under the curved pole faces, EDC is VBL, except at the instant when it reach 360 degree or 180 degree, at that instant, EDC is 0, all right? So similarly for segment DA, which is similar to the segment BC, okay, for segment DA, of course, there will be no voltage also induced, all right? So let me just redraw it again. As you can see, the segment DA, which is this segment, D to A, this segment is also 0 voltage, no voltage induced. Okay, all right. So segment DA is no voltage induced. So we can say that the total voltage. So the total voltage, the total voltage can be calculated by using this equation, which is the sum of voltage induced at segment AB and also the voltage induced at segment BC. Segment BC, which is East CB. Sorry, AB, BC, CD. Okay, EDC, right? All right. So the sum, which is the vector is in the same direction for these two vector, okay, instantaneously happen, and then we can sum up these two voltage induced. All right, so it becomes 2 VBL. Okay, 2 VBL. As you can see, for the behavior of the machine we are talking about now, it is actually, as we can observe, that what happened inside that machine is actually something like this. As you can see in this bottom figure of the output of induced voltage, it starts from 0, which is from this sort of state. Okay, so this is segment AB, and then CD at the top. So it start from here, which is 0. Okay, and then under the curved pole faces, which is this sort of arrangement, the total induced voltage is 2 VBL, which is almost a long period of time, as you can see, with 2 VBL, and then it drops when it reach 180 degree and also 360 degree. At 360 degree and 180 degree angle, it turns to 0 and then turns to negative when it reach 270 degree, around, for example, 270 degree, somewhere here, right? Somewhere here to 70 degree, it will be negative VBL at segment AB, and then back to. So we can say that the output of the induced voltage is behave like a sinusoidal voltage waveform like this. Okay, then this part is actually, we are going to calculate the similar thing. We are going to expand the resultant 2 VBL, induced voltage equals to 2 VBL here. We are going to extend that equation. So we have E in equals to 2 VBL, right? Now we are going to extend this equation, okay? This equation using the surface area, okay? The pole surface area and also the rotor surface area. We are going to relate the pole surface area of pi RL and rotor surface area of 2 pi RL, and also the relationship of the tangential speed or tangential velocity, which is V equals to R omega. We are going to substitute all of these values to have a look what happened to this equation. When we substitute all of these values to this equation, what happened to the equation of induced voltage here? So basically, the pole surface area AP here is pi RL. Why is pi RL? This is actually comes from here. For this is, for example, this is the rotor. So this one is rotor, okay, and the other one is stator. Sorry, this is not rotor. So this is rotor, okay, this is stator. Stator only give one side, okay. For example, this is south side of the stator, okay, south side of the stator, which is this side. All right, half of the curve here is 2 pi r, right? 2 pi r divided by 2, because half. All right, so it is half of the, for this curve, this particular I hope that you can see I am drawing now. Oh, I spoiled everything. Okay, so at this particular curve pole faces, the south side of the curve pole faces, as you can see, it is 2 pi r divided by 2, half of it, right? And this particular north side of the curve pole faces for the stator, it is another half. All right, so we can say that this particular pole surface area for the stator is pi RL, pi R times L, because the length of the stator is L, which is the same length to the, let's say this is, I hope you can see clearly in this figure. So the length of that particular segment of wire loop is L, okay? So meaning that we can imagine that it is the same length to the this width of the stator pole. Sorry, okay, stator pole, south pole of the stator, okay, and this particular width is also L. So for the stator surface area, it is given by 2 pi r, sorry, 2 pi RL divided by 2, okay, which is, this is the stator pole surface area, AP. For the A, which is rotor surface area, it is 2 pi r times L. Why 2 pi r? Because we are considering the full, not half, the full length or the full length of this uh, round shape, what we can see. Okay, the full length of this, the parameter, or the what we can see, the perimeter, the parameter. Okay, so this is 2 pi r, right? We know that for the round shape here, this is 2 pi r. Okay, and then times L, which is the length of the rotor, the width of the rotor, right? So that particular area is 2 pi r L. Then using that AP and A, okay, using that AP and A, what we are going to expand is this equation. Earlier, this equation was 2VBL, right? And then we substitute V with R omega. We know that V is R omega, as you can see in this one. So V is R omega, which is the tangential speed or velocity of this particular cylinder, right? So V R omega, we substitute V R omega, it becomes V R omega BL. Okay, V R omega BL, and then we further expand this equation by substituting AP pi RL. Okay, we rearrange this. So AP over pi, which is RL, because we are going to substitute this RL to that particular inside that equation. We are going to substitute this RL, all right, with AP over pi, and then we will get this sort of equation for induced voltage. Okay, so and then we know that phi is BA. So let's say BA, which is we are considering AP here. So we can substitute this BA with phi. Okay, substitute BA with phi. Finally, we can observe that this particular induced voltage equation is now becomes 2 over omega, sorry, 2 over pi omega phi. Okay, 2 over pi omega then phi. Okay, this is the final equation considering the real machine, the real DC machine. For example, so this particular equation, actually we can translate from this particular equation of induced voltage, that we can say that the voltage induced across the wire loop of that particular machine depends on 3 factors. In this case, as you can see, it depends, number one, it depends on the phi, which is the flux. The stronger the flux, meaning that the induced voltage will be higher. Okay, and then it also depends on the rotational speed. Okay, rotational speed omega. Okay, so as the omega increase, if we rotate this a much more higher speed, and then the induced voltage is also increase. All right, so the third one is constant lah, constant, which is pi is constant, right? Pi is 2. Okay, 2.34, right? And then 2 divided by pi is constant. We are considering constant which represent the construction of the machine in terms of material, in terms of the size, right? In terms of the air gap, so and so forth. Okay, so these 3 factors influence the induced voltage across the terminal of the wire loop when we are talking about a simple rotating loop between the curved pole faces. Now, so now I've been talking about the voltage induced across that terminal of the wire loop, which is it behaves like a sinusoidal waveform. Now, how do we get the DC voltage out of this machine? How do we get the DC voltage out of this machine? Okay, now we are going to change this sort of output of induced voltage to the AC, from this AC sort of behavior to the DC behavior. Okay, we are going to change this sort of behavior to the DC one, like that. Okay, what we're going to do is we put the commutator and brush. So I think you are familiar with DC motor brush, right? I think you are familiar with DC motor brush, but commutator, maybe this is the first time you hear about commutator. What is commutator? It's not train commuter. That one is commuter. This is commutator. Okay, something that is rotate, which is designed in such a way to actually transform the voltage waveform from AC sort of which is initially this voltage waveform, which is something like that. Okay, which is this part already diverted because of this commutator. So as you can see, this is the design of the commutator for single loop. And for this commutator, it has brush attached to this commutator, which the contact. The brush is contact to this commutator. When this wire loop turns, meaning that at some instant, when this segment reach to 180 degree, for example, it will change polarity, meaning that at particular instant, it will change the polarity. For example, at this instance, at 180 degree, the polarity of induced voltage change, meaning that from negative to positive. So in that case, we can see that the average DC voltage appears across the terminal of the wire loop. Okay, so across this terminal, we can see that this is DC voltage. Okay, if we get if I can draw from this, actually you can observe that the DC output, which is something like this green line. Okay, the DC output, which is, if we take the average of this particular waveform here, so basically we can get this is the induced voltage, which is DC, right? So I think that's all to be covered in this session, in this 1 hour session. So basically, to further understand on the how commutator works in DC machine, let we have a look. I think I would like to share a video with you guys within this maybe 3 or 4 minutes. Let me just stop this. Okay, so where is my video? Okay, I think my video is somewhere in this folder. Okay, so this is the video. Sorry, I'm not sharing it yet, right? Let me just share with you guys before I play this. All right. Where is my share button? I always lost my share button. Where are you? This is my share button. Okay, let me just optimize it for motion and videos for video presentation. Okay, so let's have a look. I am sharing with you guys now the video that let's have a look at this particular let's have a look how commutator works in DC machine. So meaning that commutator is basically convert the AC behavior into DC. Automobiles and types of industrial equipment. Let me just increase the audio, right? Okay, 1, 2, 3.
And many portable home appliances, automobiles, and types of industrial equipment. In this video, we will logically understand the operation and construction of a commercial DC motor. Let's first start with the simplest DC motor possible. It looks like this. The stator provides a constant magnetic field, and the armature, which is the rotating part, is a simple coil. The armature is connected to a DC power source through a pair of commutator rings. When the current flows through the coil, an electromagnetic force is induced on it according to the Lorentz law, so the coil will start to rotate. You will notice that as the coil rotates, the commutator rings connect with the power source of opposite polarity. As a result, on the left side of the coil, the electricity will always flow away, and on the right side, electricity will always flow towards. This ensures that the torque action is also in the same direction throughout the motion, so the coil will continue rotating. But if you observe the torque action on the coil closely, you will notice that when the coil is nearly perpendicular to the magnetic flux, the torque action nears zero. As a result, there will be irregular motion of the rotor if you run such a DC motor. Here is the trick to overcoming this problem. Add one more loop to the rotor, with a separate commutator pair for it. In this arrangement, when the first loop is in the vertical position, the second loop will be connected to the power source, so a motive force is always present in the system. Moreover, the more such loops, the smoother will be the motor rotation. In a practical motor, the armature loops are fitted inside slots of highly permeable steel layers. This will enhance magnetic flux interaction. Spring-loaded commutator brushes help to maintain contact with the power source. A permanent magnet stator pole is used only for very small DC motors. Most often, an electromagnet is used. The field coil of the electromagnet is powered from the same DC source. The field coils can be connected to the rotor windings in two different ways: parallel or series.
Okay, so as you can see in that video, actually whether it is motor or generator, it works the same way, where commutator is used to convert the AC behavior inside the machine into the DC output. All right, so that is the function of the commutator, and it was mentioned in this video also about the armature. Armature means the windings of the rotor. Okay, armature is, we normally say it is armature windings, meaning that we are referring to the wire loop that we use for the rotor. All right, so that is the video. Actually, you can have a check in the YouTube. There are many more videos you can follow to understand more on the behavior of commutator, which is the use of commutator, the function of the commutator for the DC machine. So in our next meeting, I am going to continue to the torque induced. Okay, the torque induced in the rotating loop, which is when we supply the current to this rotating loop, what happened is the torque will be induced. This is something about motor action. Okay, so this is motor action.